So now we're going to talk about a library of safety implemented function loops. So we can create safety implemented function loops or SIF loops, and these loops we also have the capability of creating alternate scenarios, and those alternate scenarios will show here. This is the master one. Out of this master I can create many alternate scenarios with different variations of the original one or the master one. So, and from here, if I can say, for example, if I have another project that I would like to have this safety implemented function, it is reusable. That means that I can is repeated many times in a project. So what I can do is I can create a library, because this safety implemented function might be used also in a different project. The only thing that would have to change maybe will be the tag names, but I can create a library of SIF loops. So how do you do that? There's the file menu on top here and says export SIF loops. So you go into your hard disk, any place, you create a folder, and in this case I named this folder SIF Loop Library, and then I can export this safety implemented function. In this case, for example, for me was a HIPS, a high integrity pressure protection system loop, which is very common. So I can have different loops in a library and then import them into projects according to what is needed. So in this case, you say look in that folder and then save. So what you end up is having a library of loops, and in the same at the same time, what you can do is, instead of that was in order to do the export, but you can do also the import of that SIF implemented function loop. Right. So now I'm going to show you how to link safety implemented functions with safety implemented function. Let's assume that you have a safety implemented function loop number 1, and only I work on the final element, and I create a 1 out of 2 of 3 out of 3 elements in there. So that would be for my first safety implemented function loop. And I can see here the tag will be the input output module 1, or the solenoid valve and the XV valve 1 and 2. Then I will create a second safety implemented function. That second safety implemented function also will have only the final element, and again this one will be again the 1 out of 2, and this will be 3 SOV3, XV3, and 4. So I have 1, 2, 3, 4. In this case, I created one safety implemented function final element for each loop. So now I'm going to create a third safety implemented function loop, loop number 3. And in this loop number 3, I'm going to concentrate on creating the elements of a logic solver, for example, a 1 out of 3 CPUs. So I have a 2 out of 2 CPU with memory, and this is a configuration, maybe some type of logic solver which have some modularity inside, redundancies, and so on. But when it comes to the final element, I'm going to link those final elements to loops instead of linking them, or instead of creating elements in there. So I will link to loop number 1, and then in a 2 out of 2 configuration it will be linked to also loop number 2. And then I can create loop number 4, on which I can concentrate on the sensors, and then when I get to the logic solver part, I only link to loop number 3. Inside loop number 3, I know that there's this information here that I created in loop number 3, and that loop number 3 is further linked in a chain to loop number 1 and 2. So why would you do this? Well, if you don't do this in this way, you will end up having, for example, a very large or very certain point of view, not complex, but kind of you have to work with the bars beside your window to scroll up and down and see all the elements, instead of going into the SIF loop number 1, 2, and 3, and then loop number 4. Sometimes you have these final elements repeated many times, and it's sometimes useful to name them and then link them after, right, to different other loops and so on. So it is a feature that some people find useful for linking complex architectures from final elements or sensors and so on. So, and also I can send you this file, or you can request this file. We'll send them to you. It's already created, and you can go through it and see what it was done inside there. So that file is a project file, right? So, and we know how to import and export project files. So here is what you will find in that file. So you have the project, which is called link, description, and then I have here the center, the logic solver, the 1 out of 3 of 2 out of 2s, right? So the way that you do, for example, to add the final element, this will be loop number 3. So loop number 3, I have to link loop number 1 and 2. So here's the, in red is marked the add link button in this case. So you go and add that link loop number 1 and number 2. And there is again a video in the network, or is a video that you can watch in more dynamically how is this done, not in a PowerPoint presentation like I'm showing you. But you will do that with the add link button. You add your link number 2. There will be a small screen that comes up on which you choose which loop you want to link to. So, and then automatically will calculate that probability failure on demand coming from those 2 loops, which is important. That would be loop number 3, and then in loop number 4 I'm going to link loop number 3 in there. So this is just following the same sequence of things that we did before, but this is looking at inside SafeGuard Profiler, and this will be what we call loop linking, or safety implemented function loop linking. So also you can look at the reliability block diagram graphics, and it is the same. So you have you were working on your loop number 4, final loop number 4, and you have your sensor data link, the logic solver linked to loop number 3. Loop number 3 was already linked to number 1 and 2. So now we're going to go into what is called contingency planning and risk exposure. And as I said before, remember that you can always go and look at and watch the videos or the animations on how to do this loop linkings and so on. So here, from the point of view, if the risk posed by any known dangerous initiated event or cause is increased by the loss of an independent protection layer. So we saw before that we assign layers of protection to causes, right? So what happens every time that you add a safeguard? That means that you reduce the likelihood of that event or hazardous event from happening, right? But in this case, what happens is that event, it is not there to fail, or the independent protection layer is not there, it's already failed. So that means that your risk went up automatically. So what happens if you lose a safety independent protection layer? What happens is that you're going to be running with a gap. So you don't want to do that. So therefore, contingencies or any other mitigation planning to counter on the missing IPL is required. Okay, so that's contingency planning. So think about all those safeguards that you lost. What can you do in addition to keep running, so safely keep running, and not having to shut down if there is a contingency plan. Otherwise, you will be confronted with the possibility that you need to shut down if your risk is too high, if your risk is not tolerable. So the detection of independent protection layer loss, it doesn't matter how you detected the loss. As soon as you realize that it's not there, then you have to come up with the contingencies. So you could need a contingency plan. So what are the characteristics of this contingencies planning or contingencies that are there just to cope with the loss of an independent protection layer? So this contingency plan is in a sense of another safeguard, and it again has to have all the characteristics of safeguards, but there are certain characteristics of these safeguards that are not part of the original safeguard that was lost, right? So first of all, they're not often used and are specific actions to achieve or maintain a safe level of risk when it was lost, when you lost that IPL. So, and they are time bound. They are not forever. So they are just interim, just while you're restoring your system to normal conditions and you want to keep running. So, and they have a higher priority than normal operating procedures. Of course, now they become a safeguard. So there's something additional that you're doing that is a safeguard. They are used to cope with specific dangerous situations, and they are part of the IC 61511 section 11.3 when they talk about requirements for safety behaviors on detection of a fault. So at least for a safety implemented function, if you are complying with IC 61511, you must find a contingency for every safety implemented function that you have, and it has to be the same seal level. And if you don't find any, that means that your process has to shut down. And usually that's what happens when you see high integrity level SIL 3s, for example, on your systems or your processes. What happens is that most of the time they just trip your system and shut down this facility or shut down that part of the process, because it's not easy to find that contingency plan equivalent with a SIL 3. So how do you respond? This is the flow diagram for how you respond to a fault or a failure in your independent protection layer of your process, right? So you're working in normal safe state, and after that safe state, for example, somehow an IPL fault is detected. An independent protection layer not being available is detected. It doesn't matter by which means you detect that, it's just not there. So then you have your question, what can be done if an IPL fails? Should I shut down or continue to run? If you, first of all, you get an alarm and then you look at the risk. Is the risk tolerable? Meaning, do I have enough risk mitigation at this moment, or am I exposed to risk? If I have enough risk mitigation, that means I repair the faulty independent protection layer and nothing happened. I go back to normal running safe process. Now, in this case, that if the risk is not tolerant, then do I continue to run and I implement a contingency plan if I find one? So when that happens, you say, well, no, I don't have a risk tolerant system. That means you ask yourself, what needs to be done to continue to run and operate safely? Is there any adequate alternative to do that? For example, could I monitor and apply and implement a specific procedure to supply that risk reduction that was lost by that independent protection layer? If the answer is yes, then you implement that contingency and you restore your faulty independent protection layer to final or to full functioning, right? So then again, what that happens is, how long should the contingency plan be in place for to be effective? So that means what happens if your mean time to restoration went through and you haven't fixed your problem yet? So what do you do then? So then you ask again the question, what needs to be done this time that has passed and this IPL is still not available? So you are again with the decision to shut down or not, but this time the decision is more pressing than before. Now you're being exposed to a situation that you don't want to too much. You're exposed more than maybe desirable. So you're confronted again and again to whether you shut down or you continue to run. If you repair your safeguard within that specified mean time to restoration, then you go back to normal operations and you discontinue the contingency plan, right? So again, here's how SafeGuard Profiler looks inside those contingency plans, and those contingency plans are going to be built and they're going to be tagged, or they're going to be expanded from your layer protection analysis, where is the place that you should think about them, right? Those contingency plannings. So they are going to be scenarios appended or expanded um, to your layer protection analysis. So, and here is how it looks like. So we have our LOPA causes and we have our layer protection analysis or layer of protections assigned to the causes. And then there's a tab which is called failure and contingency table. This failure and contingency table, it is created by auto-generate failures and causes. That means that the software goes automatically and chooses all these safeguards, and then it creates a row for each one. And then it creates also these columns for full failure type, which might be partial or full, and then the risk reduction and the consequence of failure. It also appears there when there's a description. So you can click twice on this field here, risk exposure with failure, with full failure, or the failure that appears here. Is it a full or partial, depending on what your scenario is. And then it will tell you, this will change and go to failure here, and it will show you what is the risk exposure in there. And then it will go to risk exposure with solution. That means solution if you implemented a contingency. So for example, you click automatically, you click twice on the risk exposure with failure, it would fail that safeguard, the first one in there, will tell you that you're exposed now and you have a SIL1 exposure 1.44, for example, 10 to the minus 2. So you have your failure exposure there. So what do? You can implement a contingency in this case. So if you click twice in here in the risk exposure with solution, that means with manual solution. Manual solution means implement a contingency for PSV 555 shutdown. Okay, so it tells you what to do in that case. So that would be the contingency, and then with solution. And you can do for every safeguard, right? A different contingency, and of course you have different levels of gaps when you lose that safeguard and so on. So this is the moment on which you can implement that contingency. It appears here with the green diamond. So when you lose this one and you implement that contingency, your risk is going to be again reduced because you had a gap of 0.11 in this case, or 10. And then you go back to intended mode. So again, it's in black. So all these colors are also programmable into the SafeGuard Profiler software and can adapt to your facility. So that was contingencies, and the next part will be working through examples and so on. So there are going to be other videos with respects on how to do, for example, the sour hydrogen gas reciprocating compressor from end to end.